Hey everyone, today we're going to talk about one of the most powerful ideas in all of computer science, graphs. You might not see them, but they're the secret blueprint organizing our entire connected world. In this explainer, we're going to dive into what they are, how they work, and why they're just so important to pretty much everything we do online. I mean, just think about it for a second. All your friends on social media, all the cities connected by airports, every single web page connected by a link. It's just this massive, tangled web of connections. So the big question is, how do we actually describe all of that in a way a computer can understand? And the answer is something called a graph. It's actually a really simple idea. You just have a bunch of points, we call those nodes or vertices, and then you have the lines connecting them, which we call edges. And that's it. It's the official, super clean way to model any kind of relationship you can imagine. So here's our game plan. We'll quickly nail down what graphs are. Then we'll look at the two main ways to store them in code. After that, we'll figure out how to explore them or traverse them. We'll even have a little showdown between the two big methods. And finally, we'll see where these things are hiding in plain sight in your everyday life.
Okay, first things first. How do we store this stuff? I mean, it's great to have this idea of nodes and edges, but how do we turn that into something a computer program can actually work with? Turns out there are two classic ways to do it.
The first method is called an adjacency matrix. Just picture a simple grid, kind of like a spreadsheet or a checkerboard. Along the top row and down the side column, you list out all of your nodes. Then, if there's a connection between two of them, you just pop a 1 in the box where they meet. If there's no connection, you put a 0. Super simple and direct. Let's make this real with our little map of 4 cities. So if you want to know, hey, is there a direct road from city A to city B? You just find row A, go across to column B, and yep, there's a 1. That means the road is there. The best part? This check is incredibly fast. It's just one quick lookup. Now for method number 2, the adjacency list. Instead of that big grid, this one is more like a phone's contact list. For every single node, you just keep a simple little list of all the other nodes it's directly connected to. So let's look at those same 4 cities again, but this time with a list. You can see here that City A's list has B and C in it. That just means it has roads leading to both. City B is connected to A and D, and you get the idea. It's a way more compact way to store the exact same map. So here's the deal, and this is really the key takeaway. You have to pick the right tool for the job. The matrix on the left is blazing fast for checking if two things are connected. That's awesome for what we call dense graphs, where almost everything is connected to everything else. But the list on the right, it uses way less memory, which makes it perfect for sparse graphs, like a social network where you're only friends with a tiny fraction of all the users. Okay, so we've got our graph stored. Now for the fun part. How do we actually explore it? How do we find our way from point A to point B? This whole process is called traversal, and you can think of it like being dropped into a maze with a map and a couple of different strategies for finding your way through. Our first strategy is called Depth First Search, or DFS. And honestly, the name says it all. The whole idea is to go deep. You pick a path and you just follow it as far as it can possibly take you. And to keep track of its journey, it uses something called a stack, which basically works like leaving a trail of breadcrumbs so you know how to get back. The logic is pretty straightforward. You start somewhere, mark it so you don't accidentally come back to it, and then you just dive down one of the paths to a neighbor. You keep going deeper and deeper and deeper until you hit a dead end. Only then do you backtrack, pop back up, and check if there were any other paths you missed along the way. So let's imagine starting at City A. DFS is aggressive. It might immediately dive deep, going to B, and from B it dives again to its neighbor D. Now, let's say D is a dead end with nowhere new to go. The algorithm backtracks. It goes back to B, sees no other new options, then it goes all the way back to A. And only then does it finally explore the other path from A, visiting City C. The key is, it fully explores one entire branch before it even thinks about looking at another. All right, our other strategy is Breadth First Search, or BFS. Now, if DFS is like a deep maze explorer, BFS is more like dropping a pebble in a pond. It explores outwards in ripples, or layers. It checks out all the immediate neighbors first, then it visits all of their neighbors, and so on, spreading out nice and evenly from where it started. This approach uses a queue, which you can just think of as a first-in, first-out line, like at a grocery store. You start by putting your starting city in the line. Then you serve the first one in line, visiting it, and while you're there, you add all of its neighbors to the back of the line. Because you're always adding to the back and serving from the front, it naturally makes you explore everything on one level before you move to the next. It's really clever. Now, check out the difference on our map. Starting at A, BFS is much more methodical. First, it visits all of A's immediate neighbors. That's both B and C. It explores that entire first layer of connections. And only after it's visited both of them does it move on to the next layer out, which in our case means visiting D, which is a neighbor of B. See that? It goes wide before it ever tries to go deep.
So we've got these two really powerful ways to explore. DFS, the deep diver, and BFS, the wide explorer. But which one do you use? Well, that totally depends on the kind of question you're trying to answer. This comparison right here is so important. DFS uses a stack to backtrack. BFS uses a queue to go layer by layer. But here is the big one, the thing you absolutely need to remember. If you need to find the shortest path between 2 points, like the fewest number of stops on a subway line, BFS is your go-to. Because it explores level by level, the very first time it finds your destination, it is guaranteed to be the shortest possible route. DFS, on the other hand, could wander down some super long, roundabout path and find the destination that way first, totally missing a shortcut right next to the start. Now, I know this can all feel a little abstract, but the truth is you are using these exact concepts dozens, maybe hundreds of times every single day. Graphs are the invisible skeleton holding up our entire digital world. Just think about it. Every time Google Maps finds you the fastest way to get somewhere, it's running a graph search algorithm that's amazing at finding shortest paths, just like BFS. When your social media apps suggest people you might know, it's exploring that massive graph of your friends and your friends' friends. Even the way search engines find new websites is by crawling the links of the web, which is basically just a giant graph traversal trying to visit all the nodes. So from mapping our planet to mapping our friendships, graphs give us this fundamental language for understanding connections. It kind of makes you wonder, as our world gets even more connected, what new, huge problems are we going to solve just by looking at them as a bunch of nodes and edges? The blueprint of connection is everywhere. You just have to know how to see it.